Okay, let's go ahead and get started. If everyone had time to run to the bathroom, grab a coffee, get a bagel or some fruit. So I'm going to continue where we left off. I just have a couple, one or two more things to talk about in terms of overall package development and building and installing before we jump into S4 classes and methods and object-oriented programming. So first of all, I'm just going to check in. How many of you already use packages from Bioconductor in your work? Lots of people. Good. How many of you know when the next Bioconductor releases? Couple. It's on, yeah, I heard Friday. So currently the official version of Bioconductor is 3.8. The next one, 3.9, releases tomorrow. It was originally scheduled for this Tuesday. It got delayed at the last minute, but currently there will be a new version of Bioconductor 3.9 released on Monday. And I tell you this because right now, today, is the creation of the Bioconductor 3.9 release branch. So any packages that are currently on Bioconductor, they're officially basically freezing the current versions of those to push into the new release. Yesterday was the last chance to commit any new changes to that. And a couple of days before that, on Monday, was the last chance for packages on Bioconductor to officially pass our command build and our command check without any errors or warnings. And so I'm telling you this just because I just got an email during the break that they were just starting to create the Bioconductor 3.9 release branch, and hopefully your package is currently working. So I just want to go ahead to look at one of my packages, Cardinal. This is for mass spectrometry imaging analysis. So this is the development version. So you can see the link here to the current release version, which will be 3.8, and starting tomorrow it will be 3.9. And I'm just on the development page for it for the most recent version. And I just went down to build report here on my own package to look at the Bioconductor, the output of Bioconductor running our command check on my packages to make sure that everything was okay, since we are just about to talk about our command check itself. So Bioconductor will run this, this command, our command check, on 3 operating systems, on Linux, Windows, and Mac OS. And you can see here these little flags tell me that everything's okay. It can also show warnings or errors. In this case, everything looks okay. But I'm going to look at the checks, our command check for Mac OS. So you can see our command check itself goes through a lot of things. Does things like checking the namespace information, checking the package dependencies, make sure that whatever you don't have any weird hidden files or portable weird hidden files or directories that aren't supposed to be there. Checks that it can actually be installed. Does some other things like checking for non-ASCII characters. Make sure the package can be loaded. Makes for sure the namespaces follow certain rules. Looks at some of the functions. It will also check all of your documentation. So this part here is where you'll get a bunch of things yelling at you that you didn't document this function, you didn't document this argument of that other function. Looks for missing documentation, looks for the usage sections of the documentation, checks if there's any packages you're depending on that you didn't tell it that you are, checks for your C and C++ code. Let's see, checks the vignettes on Bioconductor. It actually usually runs our command check using the no vignettes option. The vignettes are already built, so it doesn't bother checking those. It takes some additional time that isn't usually worth it. Here it's given me a note that a couple of my examples are taking a little bit long to run. Looking for if there's any dependencies in my unit tests that I didn't tell it about. It runs those unit tests. I use test that for that testing. Check some other things, make sure the vignettes are there if they're supposed to be, checks the PDF version of the manual, and the final status was one note, which is not something to worry too much about, just something that it wants to draw my attention to, but no errors or warnings in this case. So everything looks good in my case. So let's go ahead and try to run our command check on this MS example package. So checking a package, there's a couple different ways you can do it again. You can either do it from the terminal command line, or you can use DevTools check from within R. R command check, you always want to give it a bundled version of your package. Weirdly enough, it does actually work if you give it the source version, but you'll typically get a bunch of weird errors and warnings, such as hidden files and things like that, that would not be there if you bundled the package first. So for example, for checking this, I'm going to change to this directory for this package. And just for example, because I'm using Git, there's a .git and a .gitignore file. On Mac, so there's a .dsstore file as well. So there's some little hidden files like that that would go away once you bundle the package. But our command check would complain about if you try to run it on this source version of the package. There's some other weird things as well. So I sometimes accidentally run our command check on the source version and get weird things that shouldn't be there. So typically you want to run this on the bundled version. So I'm going to go ahead and do this using the terminal command line. So I'm going to do R command check. And this example, I'm going to use the bundled version, this tar.gz. Just a little bit bigger again. So it's going to go through and check different things. Checking for those hidden files, checking whether it can be installed, checking the files, checking for non-ASCII characters, checking the namespace, checking dependencies. It does a little bit of checking of your R code, so sometimes it can find that certain kinds of common errors in your R code. For example, if you do something like use some sort of global variable that can't be found under usual package circumstances, and it works fine when you just source it, but it doesn't work from the package, it would warn you about something like that. Oh, I ran this without, I had rebuilt it without building the vignette, so I actually got 2 warnings. So let me go ahead and build this with the vignettes. So let me do R command build on this again. It shouldn't take too long, the vignette is pretty small. Okay. And actually, I'm going to use the no vignettes option here as well, since that's what BioConductor uses. Oddly enough, using the no vignettes option in R command check will actually complain if there are no vignettes. It just doesn't actually check the vignettes that already exist. So another thing on this checking R code for possible problems, if you use some packages that rely a lot on non-standard evaluations, so things like things from the tidyverse, things like dplyr, those can sometimes get flagged in this section because you're usually using the names of variables from within data frames to refer to the columns of that data frame in things like select and filter, and this will usually complain about those because it won't actually see a variable corresponding to those names. So that's something where you might see an issue with that. If you do have something that relies on non-standard evaluation, well, firstly, if you're relying on the tidyverse and doing that, they have their own documentation for using their tidy eval stuff and how to program with the tidyverse. But if you have other non-standard evaluation stuff, and this is not necessarily recommended, we should kind of only do this as a last resort, but in any of your .r files, if you have some sort of global variable or some kind of variable that you know will exist when the code is actually run, but isn't obvious from the code itself that it will be there, you can declare that with this global variables function. I have that here in Cardinal for one such variable, just to get rid of that warning that rcommand-check will give you otherwise. All right, so let's go back here. This rcommand-check ran okay, so everything looks good with this MS example package. Now let's going to go ahead and go look at something that will produce errors. So I'm going to go back to R. Now I'm going to go ahead and use DevTools. So let's see, let's try to check this. Well, first let's build the package template 1. So this is the package template I think that we created from use this create package. And now we can use DevTools check to check this. This is not a directory, so it looks like DevTools check is actually expecting the source package rather than the bundled version. So this is another little difference between the DevTools version of these tools and the terminal version of these tools. I always forget exactly what those are. So in DevTools, the install and check functions actually want the source version, and it will build the package itself. When you're using the rcommand install and rcommand check, those typically want the bundled versions.
Quick question.
Yes?
So for your Bemis example, tar file that you have in the folder, does the package run for the latest version of R2.6 or it's for R2.5?
So that when you're installing and building and checking the packages, it will use whatever R version you currently have installed and are running when you do all of this. I suppose it is technically possible to have multiple versions of R installed, so it will use whichever one is that you get when you type R and hit enter.
So suppose in my R session it is the latest version of R2.6. So I am in the directory where we have this .tar file, and then I'm trying to install that package from that tar file. So just install that package is good with that name.
Yes. Well, you would be install that packages. You also have to set repos equal to null. So I'm going to install packages. Package.
Well, I was talking about the MS example that.
MS example.
Yeah, MS example package.
To install this with install packages. Okay. So let's do that. So where am I? I am somewhere totally different. Okay, now my working directory is in my projects folder where MS example lives. I'm going to use install.packages to install the bundled version of MS example. And I can just do that by giving it the .tar.gz. I do also need to set repos equal to null, or it will try to find this on CRAN somewhere. But otherwise, it just installs it and works the same way as if I used rcommand install elsewhere. So install.packages can also install things from the bundled version as well. So that's actually the only one of these steps that you can do from within R without using DevTools.
It won't get if you have missing dependencies, it
Right, so the issue was that if you use install packages like this, or else when you install packages from CRAN or from Bioconductor, it'll make sure it'll download whatever dependencies and things like that you need, and check all of those. Doing this won't do that. You'll need to have those already and take care of that yourself.
So for this case, what do we do for it?
Well, this package doesn't have it.
Oh,
Well, it does. I just already have them installed. So here, this relies on prot generics and S4 vectors from Bioconductor, graphics, methods, and stats everyone should already have, but prot generics and S4 vectors are two Bioconductor packages that I happen to already have installed. If you don't have these installed already, then installed packages will fail. So you do need to make sure you actually have you have to make sure you have whatever packages your own package depends on, or whatever source package you're installing depends on, in order to install it from source like this. Okay, so here we were trying to run our command check using DevTools on this package template. We found out that unlike the terminal command line version of our command check, DevTools check actually wants the source directory version. We can see the output from our command check passes the first few things okay. We have a non-standard license specification. I'm not sure why that is. And surprisingly, that's the only error. I guess when there's nothing actually in a package, surprisingly, and it will be okay. I guess there's nothing to document, so it doesn't need to warn us about any missing documentation or other things. So it looks like the package template created by create package has nothing in it, but it somehow works. Let's try the one that we created from package.skeleton. Again, we got the non-standard license thing. Got some issues. Yeah, so now we have some issues with the default documentation files that it sets up. So we can see some errors with those. The examples don't actually work. We need some actual text to be in our documentation, and so forth. So when our command check actually finds things, you get some sort of error, potentially some warnings, and sometimes a note. Notes you can decide on your own whether they're worth addressing. Any warnings or errors you always need to fix before CRAN or Bioconductor will accept that package. Any general questions on our command check, or checking a package in general? All right, so the last thing we're going to do in this section is we're just going to go ahead and install this example, which we actually already did using install.packages. packages. We'll just go ahead and try the DevTools install as well. Again, this one is a little bit different than the R command install or install.packages, because here install from DevTools actually wants the source version. I'm in a different directory, so I'm just going to go back over here and use and install MS Example with DevTools over here. You can see that I'm kind of switching back and forth between RStudio and just Terminal and Sublime Text. So, and this is something that's, again, user preference. RStudio is a pretty nice integrated development environment, or IDE, for working with R. It's totally not necessary. It makes lots of things nice, like it gives you that knit button for knitting R Markdown documents. It automates a lot of other things. It lets you use RStudio's package or project system to kind of manage little R projects that you might have. But you don't need that either. Personally, I just use Sublime Text to do most of my text editing and run most of my stuff in Terminal.
So for the function, for the installing, we installed our packages, we use repos to get
right, so install.packages, I'm giving it the bundled version, the .tar.gz version. I'm setting equal to null so that it knows this is a local package and I'm not trying to get it from CRAN or anywhere. DevTools install just expects the actual directory that I'm trying to install. So here I'm just giving it MS example because that is the name of the directory, the actual source directory that I have here. So if I originally got the package as a .tar.gz, I would uncompress that first and then use install because for some reason DevTools install uses.
So with one of the other comments that we already went through, just to unzip the objectOriented. So I'm just trying to take the first step. We have just the target file, .tar file.
If we just have the .tar.gz file, if we just have that, then I would probably just go ahead and use install.packages or rcommand install from the command line. So the other way we can do this is just rcommand install MS example here. So this is doing essentially the same thing that install.packages.
I was just trying to understand that with the alternative development. I did work from my computer with the installer packages and then calling it with the library.
Yeah, it's a little bit confusing because DevTools does everything just slightly different enough to be confusing. So this is kind of one of those things where you choose which method you like better and kind of stick to that one. So personally, I like just burning stuff from the command line. Lots of people like DevTools and just stick with the DevTools functions. All right, so we have installed our little example package. We've checked it, and everything looks good. So that kind of wraps it up for our very general overview on package development. Do we have any general questions about anything we just covered, including building and installing packages or any aspects that go into the package, like the documentation, R code, things like that. So one thing that has kind of come up a couple times is this difference between the DevTools and Roxygen way and the just command line R command way. And again, all of this is kind of something that is entirely developer preference. Going back here. So again, all of these DevTools, Roxygen 2, these things are designed to try to automate some things and make your life a little bit easier. Lots of people do find that it's easier or prefer having their documentation next to their functions or being able to install and check packages from within R rather than having to jump back to the terminal. All of that's entirely valid, and if it makes your life easier, please use these. If you feel like you don't like them or they end up making your life harder, then just don't. Again, trying to use both ways at once can sometimes lead to a little bit confusion because they do things in slightly different ways. But you should use whichever one happens to appeal to you most and the way you like to do things. Any final questions on this section before we move on to object-oriented programming? Yes.
So why is the MS example not in my user library?
So you should.
I installed it and it's loaded and I see it when I search, but it's not in the user library in R.
So
It doesn't display there like along with other packages that I have.
you mean, are you able to?
I'm able to load in everything, it just doesn't show up in the list.
What list?
It's here.
Have you probably since that's something that's so this list of packages, that's something that RStudio is showing you. So I'm guessing that's maybe the next time you start RStudio, it will
Okay,
show
just
up there.
not a big deal.
Yeah. So that's my guess. I'm not sure, but my guess is since that's something that RStudio is creating or showing you, RStudio probably sets that up when you start RStudio. So probably the next time you open RStudio, it should find it.
I just wasn't sure if there was a difference in start package from your computer or from my computer.
There should not. No, there should not be. So once you actually have it installed, if you're able to load it with library, it should be installed in the same way that you've installed any other packages. The main You can install packages to different libraries, and again, the main time that happens is all of the packages that come pre-bundled with R will be in their own library, and most of the packages that you install separately from CRAN or Bioconductor or like this will be in their own separate library, but other than that, there should be nothing distinguishing them.
R, at least past versions, if I install from the menu in R, they go into the same library as the bundled R packages. But RStudio puts them under the user profile.
So there are some ways that you can control all of this. So when you actually use install.packages, and ultimately so we're talking about some things that GUIs are handling, so like the RStudio or the R Windows app or R.app on Mac. These will have their own ways of installing packages. Ultimately, they're typically calling install.packages somewhere, and install.packages has lots of options for controlling how and where that package is installed. So you can specify somewhere in here, lib, you can specify here the library where you want to install the packages when you first install a package. So this is all something that you can control when you install packages, and I imagine the GUI apps like RStudio and so forth are doing kind of their own thing when they install packages, and I don't claim to have any idea exactly what they're doing, but they will set their own options when they install packages for you.
Is there any way to find out what it's using as its default?
I have no idea.
Yeah, so .lit paths. So if you go down to the library thing, it's right down. Yeah. So at the very end of that blurb, that's that function there spits out the vector of where it will attempt to both find and install packages, and it'll start from left to right. So she has two there. She has her user library up on the top there, and then that bottom one is the hardcore like bundled libraries. And then you can have more than two things on there. Sometimes if you're on a cluster, there will be a site library, which is like things that you share with other users on the cluster rather than things you install yourself. But if you do that, the first one should be where the package that you just installed went. And that may or may not be the directory that RStudio is showing you. But that's how you can both control and see where packages get installed.
Yep, so here we can use .libpaths. This will list whatever libraries you have. As you pointed out, I have my user library here. This will show up first. This will be the default place where packages are installed when you use install packages. You can also see I have where all of the original R packages from R were installed as well. You could have additional options here if you have multiple libraries. Usually will just be two. But this is one way of checking where things will be installed by default, and where RStudio or R.app or the Windows R GUI are actually putting your packages. Any other questions? Okay. Thank you. Okay, so on that note, we're going to leave our MS example package behind for just a little bit. We will come back to it later and explore in more depth what functions it's defining, what methods it's defining, and what classes it's defining. But now we're going to take a step back and talk a little bit about functions in R in general, and then get into object-oriented programming, including S3 and S4 classes, which bioconductor uses extensively. It uses S4 classes extensively, and they are also used in the MS example package that I showed you. So again, some references for you. So there's this advanced R textbook by the same author as the R packages textbook. Again, this is freely available at this URL. So it just has a few chapters on functions, functional programming, and object-oriented programming in R for some of the topics we'll be talking about right now. And of course, if you want the full details on absolutely everything in more detail than you can probably handle, you can read the R language definition by the R core team for more details once you feel prepared. Okay, so let's talk about functions and object-oriented programming in R, starting with functions. So John Chambers is the creator of the S language. For those of you who are unaware, S was the predecessor language to the R language. R was essentially created as an open source version of S. The S kind of stands for statistics. When they, interesting fact, when they were first creating the language S, they originally wanted to call it SAS for Statistical Analysis System, but that name happened to be taken by another piece of software at the time. It was also created in AT&T Bell Labs, so they decided to name it after a single letter. AT&T Bell Labs came up with another language called C. In this case, they went with a different letter. They went with S for statistics. Robert Gentleman and Rasi Hihaka later created the open source version of S that we use now called R. They essentially just went one letter over from that. Appropriately enough, it was also the first letter of both of their first names. But John Chambers eventually became a core R member as well, and has contributed very much to R itself as well, as well as being the creator of S. So we should take whatever he says kind of to heart here. So to understand computations in R, says John Chambers, two slogans are helpful. Everything that exists is an object. Everything that happens is a function call. So we're going to spend the next couple of slides understanding exactly what each of those two statements mean. So first, everything that exists is an object. So we're going to look at a couple of very simple lines of code here. So who can tell me in simple terms what's happening here? It shouldn't be too hard yet. Anyone?
Adding X and Y.
Adding X and Y. Is that all that's happening?
You created two objects and then you combine them with a plus operator.
Yeah, so first we're assigning a value 2 to a variable named X, and then we're assigning a value 3 to a variable named Y, and then we're doing X plus Y, and we get the number 5 printed out. So that seems simple enough. What actually happens when we do this? So everything that exists is an object. So let's take this expression X plus Y, and then just use this little quote function to kind of capture that actual expression. Rather than evaluating it, we're just essentially capturing that language X plus Y. And we can actually check what type of object this X plus Y object is, and we can see that it's a language object. And type of will just return an object space type. Here X plus Y is a language object. And what this is telling us kind of is that the R code itself is essentially an object that can be manipulated and changed and evaluated at will if we know how to do it. So there is a function called eval that will evaluate whatever R expressions we give to it. So this SEXP variable that I created with the language object X plus Y, this is an expression that we can evaluate with eval. So if I call eval on this X plus Y, it will do X plus Y and give me the value 5. But I can actually change this language object itself. So I'm going to go ahead and actually do that over here. So at the beginning, we had 2 assigned to X, 3 assigned to Y. We added them together. That part seems obvious enough. And then we created this little expression, this language object x plus y that we call SEXP. We check that it's a language object. See what it looks like. It just looks like code. If we use the eval function on it, it will evaluate to 5. But now let's actually try changing it. So I'm going to assign something into the first element of this SEXP object. I'm going to assign another language object. I'm going to assign this asterisk language thing. Now if I look at what this SEXP is now, the language has changed. It's now x asterisk y or x star y. So what do you think we'll get if we do eval now? Yeah, we get 6. Okay. Okay, so what we've done is we've actually changed this language object. We've manipulated essentially the code itself. And we've replaced that plus operator with an asterisk now, which is multiplication. To see exactly what this looks like in kind of a kind of object that we're more familiar with, we can course this to a list. And what that looks like now is it looks like the first element is now this star or asterisk operator. The second element is name x, and the third element is a name y. And so where did this come from? Well, we assigned it, and another question is, why does it come first in the object? When we print it out, it looks like this, right? X star y. But when we turn this into a list, it's actually the first element. We put it there by assigning into the first element. So does anyone have any ideas why it's the first element there instead of the second element? The name of a function that we're using. So what exactly happens? So everything that happens is a function call. So when we're using x plus y, that's actually this entire thing. So we're assigning the value 2 to x, the value 3 to y, and then doing this x plus y thing. What all of these are actually doing is essentially calling these functions, this assignment operator, this next assignment, and then this plus function. So we can rewrite everything we just did here in something that looks more like the way we would typically call functions. So we can actually call this assignment operator as we would call an ordinary function, to assign 2 to x, to assign 3 to y, and then to do addition on x plus y. And so that's what's actually happening internally, and that's why the plus, or in our case, what we've changed to be the star now, is actually the first element here. So in R, addition and lots of other things that we do here, like this assignment operator, these are just functions. And normally we would use the, and here we're using the infix notation, which just means that the function actually comes between the arguments. And normally this is the prefix notation, which other functions typically use, but in this case it's kind of weird to write it that way. It's not what we're used to, but they're essentially just functions that are doing the same thing, so we can call it this way as well. And that's why we accessed this star or the plus operator by accessing the first element of this SEXP object. So functions. Functions in R are first-class citizens. That means they're objects. Everything in R is some kind of object. We saw that the language itself can be manipulated as an object. Functions can as well. Functions can be passed around and manipulated like any other object. In particular, functions in R have 3 particular characteristics. They have a body, which is essentially the code inside the function that actually does the thing. It has formals. This is the list of arguments used to call the function. So these are your parameters for the function. And then one other thing that R functions have that not all functions have is an environment. An environment tells the function where we can find the variables that this function uses. And this isn't something that we typically think about. Sometimes we do, but usually we don't have to, because we usually just specify the body and the formals when defining the function. We usually just specify the parameters and the actual code that the function uses to do whatever it's doing. The environment is defined automatically by essentially wherever you are when you define the function. So, and we'll come back to that in just a moment. But let's create a very simple function in R. I'm just going to create a function called add. Create that using this function. Takes two arguments, x and y, and we're just going to add them together. We can extract the body of this function with the body function. You can see it's just x plus y. We can get the list of formals, so these are the formal arguments. We can see they're x and y. They have no default arguments. If they had any default parameters here, they would show up here. And we can check the environment. In this case, the environment is just the global environment. And that's because we created this function in the global environment. That's where we usually are when we're writing our code. So the environment is just defined automatically by wherever you are. Usually that's going to be the global environment. One exception to all of this are primitive functions. There are some low-level primitive functions that are defined by the R core team that behave a little bit differently. They call C code immediately. Essentially, they don't have an actual body. They just essentially go straight into C code. Primitive functions only exist in base R. Only the R core team can create or modify those. So we're not really going to talk about them any further because we can't do anything about them. I'm sure Gabriel can tell you a little bit more about primitive functions if you're especially interested in them. Okay, so defining a function in R, we're defining simply by the function. Whatever arguments we give to that become the formal arguments of the function. Whatever expression follows that, in this case just x plus y, becomes the body, and whatever the current environment is becomes the environment for the function. And usually if you're just writing R code and evaluating it interactively, that'll usually just be the global environment. That's not always going to be the case. That's something that's typically defined automatically, and usually it's the global environment. Note that while you can explicitly return values with the return function, and if you're coming from some other language that does that, like C or Python or something, you may feel the need to do that. R does not require it. You don't need to explicitly return values. R will just return whatever the value of the last evaluated expression. Return itself is actually a function that can potentially slow down your function by fractions of picoseconds or something. So there's no real need to explicitly return anything unless you specifically want to escape from a function early or something like that. So a function will just return the value of the last evaluated expression. Another thing that is not unique to R, but is used a lot more often in R than you might use it in some other languages, is that you don't actually need to assign functions to a variable name to use them. Functions are not bound to any particular name or any particular variable or anything like that. A function is just a function. We can pass them around as much as we like, and we can actually evaluate them without giving them a name at all. So here, I just have a function xy that does x plus y. That's a perfectly valid function on its own without assigning anything to it. And I can use that function without assigning it to any variable at all either. So here I just have it surrounded in parentheses, and I'm calling it by giving it a list of parameters enclosed in parentheses. And you can see it's doing 1 plus 2, and it's giving me 3. So I don't actually need to assign it anywhere in order to use this function. This is called an anonymous function, and these are especially useful when you're doing some sort of functional programming using functions like lapply, sapply, or the map function from per. These are all fairly common ways to operate on either lists or vectors in R.
Now, how do you find out what its environment is if it's an anonymous function? I'm asking because I think it's integrate, but necessarily find things that I thought it would find unless I passed them explicitly as arguments.
Right. So that's a little bit difficult. Again, the environment will be defined automatically by essentially wherever you are. If you're just, in this case, because I'm just doing this on the in the global environment, the environment will be the global environment. But if you're doing this, say, inside of another function, then the environment will be the temporary environment that that particular function created. We'll talk a little bit more about that in just a minute. So probably when I get to that part, I'll revisit this question in just a minute. Oh, it's actually right now. So the question is, yes, how does a function find values for the variables in its body? So here I'm just going to create two simple functions. The first one is called add1. It takes an argument x. It adds 1 to x. Fairly straightforward. I can use it on 1. It'll add 1 to 1 and give me 2. Now I'm going to create another function. This one's called add y. It takes one argument x, and it does x plus y. So do the first one. That seems straightforward enough. Now I have this additional function, add y. Now if I do add y on, say, 1, what's going to happen? Anyone have any ideas on what this will return, if it will return anything at all? Any ideas?
1 plus y.
1 plus y. It will return 1 plus y, potentially if it can find y, but what's y?
Read from earlier.
Yeah, that's actually what happens. So we have, earlier on, we defined in the global environment, we assigned 3 to y. Right now, we created add y in the global environment. So if I do x plus y, that function is still going to be able to access the variables in the global environment. We already have a variable y in the global environment, so it uses y equals 3. Add 1 to that, and we get 4. So what happens here is functions capture the environment in which they were created. In this case, we can see that was the global environment. We can use the environment function to check the environment that a function has. Of course, for that we have to be able to access the function itself in some way, either as a name or the anonymous function itself. But here we can see that this was the global environment. That means if we update y in the global environment and call add y again, now we get 3. And so that seems a little bit weird, but that's the way that R works. And there are ways that it can be useful. In this case, I'm not sure, because we can just change y to whatever we want it to be, and because this function can see our global environment, it might change the behavior. But there are some reasons that we might want to do this. So for example here, suppose we want to create a function that allows users to add some number of value to any number. And we want to create a function that creates a function that does this. But we don't know what val will actually be when we're going to write our function. We want the user to be able to give this value to the function that we write, and they will get a function in return that does what they want. So we want a function that returns a function that does something different. A function that returns a function like this, or takes a function as an argument, is called a functional, or a higher order function. These are particularly common in R, especially in functions like lapply, sapply, and these sorts of things. So here I'm going to create a function called addVal. It takes one argument val, and it returns a function that takes an argument x and returns x plus val. And so now this is addVal. It returns a function. I'm going to use addVal on 10 to create a function called add10. If I just look at add10 on its own, if I look at the body here, I can see it takes I can see it takes x and it does x plus val. I have no idea what val is apart from the fact that I just created it as 10. But now if I do add 10 on 1, it'll give me 11. If I do it on 2, I'll get 12, and so forth. And I can see, in this case, the environment for this function that was returned to me, this add 10, the environment for here is not the global environment. So typically, with functions that we have in the global environment, it doesn't usually print the environment by default. For any other kind of function for any function that does not have the global environment, by default it will tell us what that environment actually is. And in this case, it's just this identifier for the environment that this function actually uses. So what exactly happened here? So we're going to take a moment and think about exactly what happens when you call a function in R. So whenever you call a function in R, the following happens in this order. So a new temporary environment is created. So you have a new environment. Any formal arguments from the function are assigned into the temporary environment. So in this case, when I call add val 10, it'll create a new temporary environment. In this case, this temporary environment. It'll take the formal arguments of add val, in this case val, and it'll assign those into this temporary environment. So this environment will have a variable named val with the value 10.
Very kind of question on that.
Yes.
Since you didn't assign it to an object, it's already gone?
It should be, yeah. Oh, yeah. Yeah, in this case, so here, the first one I assigned to add 10, so this part here is still lingering around. This one right here I didn't assign to anything, so it should be non-existent now.
It's actually still there for until you run something else. So there's a variable called dot last dot value with the L capitalized, and that always has the last value that came out of the REPL. So what this means is that if you forget to assign something to a variable, you can grab it as long as you don't assign anything else. But in one expression, then it will be.
I knew you were going to jump in with something there. Yeah, so as far as you're concerned, you can probably think of it as being gone in most cases, because you're probably going to then run some other code. But yeah, so there is the circumstance where it is technically still there for a little bit longer until something else happens that then gets rid of it. That's not something you usually need to worry about until you do.
There's only one step back in the stack.
All right, so we have a new temporary environment that is created when you call a function. Any arguments from that function are assigned into that temporary environment. This temporary environment's parent environment. So every environment has a parent environment. So if you're in one environment and you're looking for something that's not in that environment, you go look in its parent. So this temporary environment's parent environment or enclosing environment is the function's environment. So in this case here, add val, when I call add val 10, it creates a temporary environment that val is assigned into. And this environment's parent environment is the global environment because that's the environment for add val itself. The function is then, the body of the function is then evaluated in this temporary environment. Whenever a variable name is encountered, R will search the current temporary environment, then the parent environment, which is the function's environment, then that parent's parent environment, and so forth until the variable is found. So what that means here is when I create this add 10 function from add val, it creates this temporary environment, and since I've assigned the output of add val 10, which is a function, I've assigned that to this add 10 variable name. This environment, which would usually go away after we do some other things, sticks around. So this environment actually still exists. It's no longer temporary unless I get rid of this variable. So this environment sticks around, and this environment still has val inside of it. So here, I still have my add 10 function with its own environment, and I can look inside that environment just using ls like I normally would, and I can see that that value, that variable val is inside that environment. And that's how add 10, when I use add 10, that's how it has access to val here, because it still has that environment with that variable in it. So when a function is stored together with its environment in this way, it's called a closure, because it's essentially enclosing any variables that you give to it so that you'll have access to them later. There's a lot more things that we could talk about in terms of functions. Those were some of the main things that I wanted to cover. The advanced R textbook chapter on functions will give you some more information for things like stuff on default arguments, missing arguments, lazy evaluation, special calls and fixed functions, replacement functions, and so forth. That's all I'm going to cover right now, so that we have some time to talk about object-oriented programming. Are there any general questions about functions and what we just talked about now? Yes?
Is it only X from a global environment in the example you showed?
For add 10 here? For this?
Yeah.
So here for add 10 is a function that takes the argument x, so one of its formals is x, so the x here is whatever I give to add 10 here. So remember, so if I call add 10, I'm going to give it, say, 5. So the first thing that will happen when I do add 10 on 5 is it will create a new temporary environment. Any formal arguments of that function will be assigned to that temporary environment. So x will be assigned into the new temporary environment with the value 5. And then the function will be evaluated. The x there will then be the x in that temporary environment, which has the value 5 from what I gave to it as the parameter here. Does that make sense? Kind of? Yes.
Are those environment names meaningful at all? Can you use them at all?
I mean, you can. I mean, they're useful in some ways. I don't think the actual hash identifier for the environment is useful on its own. You can get a reference essentially to the environment and pass that around if you happen to need to reference that environment somewhere else. You can actually index into environments kind of like you would a list. So I can use $val here to get it. You can index it like this as well. Environments have no concept of an ordering those, so if I can't do something like this. But on its own, this on its own isn't particularly meaningful, at least in a way that we could manipulate. Any other questions so far? All right. Okay, so who here has any experience with object-oriented programming? Few people. Who here has done any object-oriented programming in R? All right, so what are some languages that you've used object-oriented programming in before? If it's not R. C++? Java, Python? Good. All right, so for those of you who are new to object-oriented programming, object-oriented programming is a way of organizing code around commonly reused data ideas, in particular classes and methods. So it's essentially a way to encapsulate certain ideas and reuse them. So a class is basically just a blueprint for a particular way of organizing data. So for example, if you've worked in R at all, you've probably encountered a data frame. A data frame is a class for heterogeneous tabular data. So lots of people will use a data frame, and the class just means that the data frame is a formal idea for the way that we're going to work with heterogeneous tabular data in R. An object is a particular instance of a class, so again, you've probably seen the iris and empty cars example data sets that come with R. These are just commonly used in examples, but if you haven't, iris is just a data frame of some measurements on flowers. Empty cars is just a data frame with some information about some models of cars. There's nothing special about these data sets, they're just data that always comes with R. But these are both data frames, and so particular instances of a class, in this case iris and empty cars, these are objects that we can manipulate and work with in the way that we could work with any kind of data frame. Inheritance allows us to create subclasses that specialize superclasses. So we have this idea of a data frame, and suppose we want something that is a data frame but also does other things as well. So we can use inheritance to say this thing is a data frame, but it's also this other thing and specialized and has certain specializations. So if you've used the tidyverse in packages like dplyr, you've probably encountered a tibble. A tibble is essentially a data frame, but that's been specialized a little bit by the tidyverse. So for example here, I'll reverse iris to a tibble. And we can see it prints out exactly like a data frame. Well, not exactly like a data frame. It prints out a little bit differently from a data frame, and that's because it's actually a tibble, but it's also a data frame. So it inherits most of its behaviors. It acts mostly the same way as a data frame does, but it has a little bit of specialization. So for example, it prints a little bit differently. And then we can define methods. So a method is a function associated with behavior specialized to a particular class. And in R, methods work a little bit differently than they do in lots of other languages like C++, Java, or Python. They're actually associated with generic functions rather than the classes themselves. So for example, in R, pretty much everyone, unless you were born with under ggplot2, most people have at least encountered the base R plot function. This is one example of a generic function in terms of there's one plot generic function that everyone can call. Everyone can call plot on something, but what actually happens when you call plot on an object can be totally different depending on what class that object is. So I'm actually not sure if there's a plot object for data frame, but if I do that, yep. So here I just do plot on a data frame, and it just creates this correlation matrix of all of the different variables in the data frame. Conversely, I could call plot on, say, just a vector of normally generated variables, and it does something different. It just plots that variable on the y-axis against the index on the x-axis. I can also plot, say, sepal length versus sepal width. And again, this will do something a little bit differently because I'm giving it a formula. I'm not actually giving it a data frame, although I am later on. But the first argument here is a formula, and so it's again doing something a little bit differently than if I just gave it the data frame on its own. So plot is specialized for whatever class of object I give to it. So there is a plot method for data frames, a plot method for vectors, a plot method for formulas, and so forth. Is that more or less clear? Okay. So let's look at a very simple example. We'll look at some more complex examples later on when we take a look at MS example again. But for now, we're just going to take a look at a very simple example. So suppose you have a pet simulator game where you're a pet owner and you have some cats or dogs or something in this game that you can play with or whatever. So this pet simulator game, if you're programming it, it might contain the following elements. You might have a generic animal class that has subclasses cat and dog, because both cats and dogs are both animals, so you want them to inherit the general behavior from generic animals. We might have a generic function called speak, and cats and dogs would speak differently, so we would have a separate speak method for cats and a separate speak method for dogs. We could have a specific object named Mittens, that's an instance of the cat class. We could have a specific object named Duke, who's an instance of the dog class. And if we say it's wanted Mittens to speak, Mittens might meow, and if we ask Duke to speak, do what dogs do, and wolf or something like that. So now at this point, a few of the differences between object-oriented programming in R and in other languages like C++ or Java or Python, if you're coming from those, is that these methods, so speak for cats and speak for dogs, these methods belong to the generic function speak rather than to the classes Mittens and Duke. So the way that you would typically call methods in other classes like C++ or Java or Python would look something like this: mittens.speak, duke.speak, where you have the object associated with a class and you call that class's method. R takes a different approach. It takes a more functional programming approach to object-oriented programming. So the methods actually belong to the generic functions, so that the way that we call these, or the way we would call any function in R, is we call the generic function speak and give it an object of class cat or an object of class dog, and it will go find the appropriate speak method for cats or dogs. And if you're coming from C++ or Java or are very used to some other object-oriented programming system, this might seem a little bit confusing at first, but it's just kind of a different way of thinking about object-oriented programming. Any questions on that in general? All right. Okay, so one of the more complicated parts about object-oriented programming in R is that there's actually multiple ways to do it. So there's actually two commonly used object-oriented programming systems in R. There's S3, which is a more simple class system. It kind of resembles the way that Python approaches object-oriented programming. It doesn't really have formal class definitions, and it's also single dispatch, which means that methods can only specialize on their first argument. They can't be specialized on any other arguments. So speak here will only care about its first argument and whether that first argument is a cat or a dog. If I gave speak a second argument here, I can't have cats and dogs speak to each other differently than I have cats and cats speak to each other. So that's one minor limitation of S3. In lots of situations that won't always matter, but it is one limitation. S4 classes are a more complex and formal class system. Bioconductor typically is probably the biggest user of S4 classes because Bioconductor is designed for handling complex biological genomics and proteomics data. So we kind of benefit the most from having more formal class definitions and having a more complex class system that can account for all of the actual complexities in real-life biological data. But in general, it's a more complex class system. You have formal class definitions. S3 is a lot simpler. You don't have any formal class definitions. S4 classes, S4 methods also have multiple dispatch, so it can be specialized on multiple arguments. So with S4, if I gave speak 2 cats, I could have that do something differently than if I gave speak 2 different dogs, or a cat and a dog. All of those could be separate methods with S4. So when should you use S3 and S4? We'll talk about both in the next few slides, but some general ideas on when to use S3 and S4. S3 is generally better for simpler data structures without complex dependencies. It's probably best for objects or for classes that users won't heavily change or modify. I say that with a grain of salt because S3 is still very successful for things like data frame that are S3 classes and people do a lot of things with them. but S3 is probably best for more simple classes that you don't need to worry as much about what the internal structure of that class looks like. S4 is for more complex data structures, so lots of the experimental representations on bioconductor use S4 because we have very formal ideas on what biological data should look like, what valid data and what valid experiments look like, what those requirements should be, so we use S4 to reflect those ideas. In general, S3 is more common in base R and in CRAN packages. S4 is more common in bioconductor. People will still use S3 on bioconductor for some more minor classes, but and by that I mean, say, if you're just returning the result of an analysis, that could be a simple S3 class. But if you're implementing a class for representing proteomics experiments or representing genomics experiments or things like that, those will typically need to be in S4 for bioconductor. There is a third object-oriented programming system in base R called reference classes. We're not going to talk about those in this class because they break some fundamental assumptions about data in R. In general, in R, you can expect data to be immutable. That is, if I do something like x equals 5, y equals x, update y to 10, x remains 5. So in R, I expect behavior like this. Even though I've assigned x to y, y is still its own thing. If I update x, y doesn't change. Reference classes don't behave the same way. Reference classes are mutable. They act more like classes in other object-oriented programming languages like Java or C++, where if you change something in them and you have another variable pointing to the same thing, you will see the exact same changes. And that can be useful in lots of situations, but it does break some fundamental assumptions of what we think about, of how we think about data in R. So we want to talk about them here. There's another R package called R6 that implements kind of their own idea of this as well. I know that I think Shiny and some other RStudio tools use that, but again, we won't talk about that. They're useful for certain things, not so useful for what we'll be talking about right now. If you want to do some GUI programming or develop a new version of Shiny, maybe you can look into those more. All right, so S3 object-oriented programming. So the S3 class system is fairly simple. It's essentially based on just adding attributes to any of R's base types, specifically a class attribute. So S3 classes are based on any of R's base types. So you can have an S3 class based on integers, based on numeric vectors, based on character vectors, based on a list. Most S3 classes you will encounter are essentially based on a list. And S3 classes are just defined by having a class attribute that can be accessed and set by the class accessor functions. So who can think of some S3 classes that you already know and probably use? I told you one already. Data frame. Oh, this is not data frame. This is data frame. So yeah, so data frames are an S3 class, probably one of the most widely used S3 classes in R. So we can see what the base type is. Internally, data frames are actually just a list. They're a list where each element has to have the same length because we expect all of the columns to have the same number of rows. We can see the class attribute. We can see it's a data frame. If we look at the full attributes for a data frame, you can see it has a classes data frame. It has the names of the columns and some row names. We can think of another S3 class. Factor. Did you say something differently? Did you say something? Something else? Okay. All right. Factor is another one. So factors are the way we represent categorical data in R. And internally, they're just integers, but with a class attribute factor and with another attribute levels that records the possible categories for that categorical data. Internally, they're actually just integers, so this would be an integer vector of 1, 1, 2, 3. But we can map those back to the levels of the categorical variable, and this is an S3 class. You can think of another S3 class. Who here has been yes? Yes, I believe they are. I don't have a slide for those, but I'm pretty sure ggplot2 objects are an S3 class, yes. So let's try to model using LM. LM returns an S3 object as well. So LM returns an object of class LM, which in itself is also based on a list. You can see that it has a bunch of different elements in that list, but the important part is the class attribute is LM. I believe ggplot2 classes are class GG or something like that. Yeah, so ggplot will return objects of class ggplot and gg. So this is actually, so with S3 objects, when you ask for the class, it can actually return a vector, and this is how inheritance works for S3 classes. So for example, let me grab the Tibble version of Iris. Where this will be a little bit more clear. So in the tidyverse or in dplyr, a Tibble is a kind of data frame. And the Tibble version of Iris is a data frame. It's also a Tibble. It's also an in-memory data frame Tibble. So the most immediate child subclass will be the first one here, and then additional elements of this class vector will be the parent classes. Any quick questions on S3 classes? We're going to talk about how to work with methods for S3 classes now.
So to summarize that, how would you identify whether classes are S3 classes? What would be the key points to do?
Well, I believe there is a function for determining that explicitly. I know there was one for there's one for is S4. Is there one for is S3?
If it's not S4.
Is not S4. Yeah. So I don't think there's one explicitly besides checking that it's not an S4 class.
I'm just trying to understand like what characteristics of it, like not able to figure out. Like you discussed about it, but just to summarize that. Oh, a quick way to check it ourselves.
So the quickest way to check what class something is just look at the class attribute. And this will tell you what class it is. It will still tell you what class something is if it's an S4 class. But for S3, this is pretty much the primary thing that determines whether it's an S3 class and what S3 class it is. And that's one of the things about S3. It's very simple, and there's no real requirements for an S3 class besides defining this class attribute.
Or in other words, what differentiates S3 and S4?
So S3 classes, like saying like they're labeled, like they don't actually demand any sort of structure. So if there's any sort of class definition, that means you're in S4 or 6. But if the question what is this class is even well formed at all, then you're in S1. If it's just like the only thing S3 classes do are decide what method statement, which is kind of but they don't actually define any structure of something at all. Whereas S4 does.
Right. The thing with S3 classes is there's no actual formal class definition. The only thing that's really defining something as an S3 class is this class thing, this class attribute. So I could do something weird that doesn't make any sense, like say x is 5. I'm going to say x is a data frame, and it will try to treat x as a data frame and fail spectacularly, I imagine. Yeah, so it will try to treat x here as a data frame because I gave it a class attribute data frame. It's not going to work correctly, but that's all that I need to do to say that x is a data frame. So that's one of the things about S3. There's no formal class definition. There's no formal checks that you can do to verify that something is actually a valid S3 class or is well formed or anything like that. It's essentially just this class attribute that gets set at some point. And assuming that you're the one that is controlling this S3 class, ideally you're going to have constructor functions and methods that the user is intended to use so that everything goes well and you don't break things. But it's very possible to just break things like this. Yes?
You do like s.dataFrame or s.factor? Is that kind of what it's doing in class? It's like assigning its class?
No, all I'm
Trying to.
actually doing here is, so x here is just a length 1 numeric vector. Every R object has these things called attributes that are essentially just ways to annotate that object. And this is stored somewhere as a list, essentially. And so all setting an S3 class actually does is it sets a class attribute here. So x here just has this class attribute set to data frame, and that's all that that's actually doing. If I actually try to do as.dataframe, it might try to do something more intelligent. X here is still a fake data frame here, so. Yeah, so if I try to actually do as.dataframe, as.dataframe is a function that's been defined somewhere to do something actually intelligent and return something that's an actual data frame. So it's doing something totally different. This is what I'm supposed to do if I want to turn something into a data frame. This is something that you can do because of how S3 works, but you should not do. All right, so how can we actually define methods for these S3 classes? So first we need to define some sort of S3 generic functions. So for example, like plot. Here I'm going to take a look at some S3 generic functions that already exist. So if you've worked with linear model objects fitted by LM, you've probably used fitted to extract the fitted values or used residuals to extract the residuals. These are S3 generic functions that will do something a little bit differently depending on what kind of model you fit. There's one method for LM, there's another one for GLM, there's another one for, say, an LME object if you fit it using LME or something like that. So all an S3 generic function actually looks like is it just is a call to this use method function that has the name of the S3 method. So fitted here, I can tell it's a generic function, an S3 generic function, because the body of the function is just calling this use method function with the name of the generic function. Same for residuals and lot as well. So all of these are just S3 generic functions. I can tell because they have this call to use method that will eventually determine what method to actually use when we call this generic function on a specific object. So we can find out what methods are actually defined for these generic functions using the methods function. So here I can see what methods are defined for fitted. There's a fitted default method, one for getting fitted values from NLS objects, one for smooth splines, one for k-means, and so forth. There's a bunch of different residuals methods as well. For example, getting stuff from GLMs. There's a default method. There's one for getting things from LM objects, and so forth. So what you can kind of see from here is that S3 methods themselves are also very, very simple in that they're just defined by the naming convention, the name of the generic dot the name of the class. So all that the residuals method for LM is it's actually just a function named residuals.lm. S3 method dispatch relies on this naming scheme to figure out what function to call. There are no real additional requirements for defining an S3 method for a particular class. There are some specific things you have to do for exporting them in your namespace in a package, but for just creating an S3 method, there's no real thing you need to do besides following this naming scheme. assuming an appropriate generic function exists. So residuals.lm is just the name of a function for the method for lm, and fitted.lm is the same thing for, oh, we actually saw that there was no fitted.lm, so that's another thing. So if I called fitted on an lm object, well, I can see there's no specific method called fitted.lm to use for lm objects. And what happens in that case, there's a default method called the name of the generic .default. And so in that case, when there's no specific method defined for a particular class, it'll use that default method. So fitted.default will be used if I give fitted some objects that's not one of these other ones. You can find the actual function for a particular S3 method using getS3 method. So if I want to find out the default fitted method, I can do that using getS3 method, fitted, and the default method. And this is what happens if you just call fitted on any object that doesn't already have a specific fitted method defined for it. And see, it just checks if there's fitted values in the names of the object. If so, it returns that. Otherwise, it returns a component called fitted, and it does NA predict on the result of that. We can also check what S3 methods are defined for a particular class by using the methods function and specifying the name of the class. So if I want to see what methods I can call on an LM object that does something specialized for linear models on the LM class, I can use methods class equals LM. I can see with an LM object I can add one, I can coerce it, I can check the number of observations, I can plot it, and so forth. Alright, so let's go ahead and define an S3 class for our little pet simulator game. So we can define an S3 class either by using structure or setting the class attribute of an existing object. Structure here doesn't do anything special either. It's just a way of essentially adding attributes to an existing R object. So all I'm doing when I'm saying structure here on list is I'm essentially just creating a new object that's just an empty list that has a class attribute animal. Structure here isn't doing anything special besides setting the attributes that I give to it as additional arguments. So if I check the class of this output, I can see it's an animal. And this is another way I can do it. So any existing R object I have, if I just set the class attribute, as we saw before, that will also do everything I need to actually assign an S3 class to it. So, as we were talking about before, since there's no real formal definition for S3 classes, you always typically want to create some sort of canonical way to create objects of that class. So here we're going to create constructor functions for cats and for dogs. So all of this will do is we're going to create a function named cat, a function named dog. They'll just take the name of that particular pet and return a list with one component called name, and the class, in this case, is a vector. We're using inheritance here because we have the class will be a cat, which is also an animal. Here the class will be a dog, which is also an animal. So do these in R. So here, cat and dog are just functions that return, in our case, a list that has a class attribute cat animal or dog animal. I can create a cat named Mittens. I can create a dog named Duke. On its own, that's not particularly useful. So let's do a little bit of customization to do something more potentially useful. So let's define a custom print method. So whenever we just type something on the command line and hit enter, what's actually happening is there is a print method being executed for whatever class that happens to be. It's the last thing we'll do before we break for lunch. So here, to define a simple print method, all we need to do is follow this naming convention of the name of the generic print, in this case, which I'll confirm here is an S3 generic, because I can see it just has use method and the name of the generic here. So print is an S3 generic function. So I can define a print method for animal objects in general. That means both cats and dogs will inherit this same print method. To do this, I just use print.animal. I give it some function that I want to be called whenever this object is printed. I'm just going to print that it's a class, cat, dog, whatever, named whatever name I gave to it. So here I have print.animal. If I create a cat named Mittens, it'll use that print method. Again, that's all we need to do for an S3 class and method. We just need to follow this naming convention and have the class attribute set. We'll create a dog named Duke, and it will also use the same print method as animal. Again, both cat and dog here inherit from animal, so they will use the same print.animal method. Any questions so far to this point? It is deceptively simple. All right, in that case, we're going to go ahead and take a break to go get lunch, and we will return here at, what's this say? We'll return here at 1:30.